In this class, we continue with our ongoing discussion on the practical transformer. In the last session, we evolved the complete equivalent circuit of a practical transformer with all the imperfections put in that. Starting from the equivalent circuit of the transformer, let us see how we obtain the phasor diagram, and then we will have a discussion on per unit values and the per unit impedances, which are very important from the from understanding the various features of the transformers. And following that, we will look at some simplifying assumptions that we can make on the equivalent circuit, so that we will be able to obtain the various impedances of the equivalent circuits from actual measurements. So, starting from the equivalent circuit of the transformer, which we have evolved in the last class, we have a source E g, and this is where the terminals of the practical transformer begins. There is first a resistance R1, which represents the winding resistance of the primary coil, and then you have a reactance, the leakage reactance due to the leakage flux. This is followed by the the magnetizing reactance and the core loss component. The magnetizing reactance and the core loss component, which is now connected to the ideal transformer like this. There is a core with ideal characteristics, the secondary of the ideal transformer, which is connected to the leakage reactance on the secondary side due to the leakage flux of the secondary ampetones. This is followed by resistance R2, which is the winding resistance of the secondary coil. This goes to the secondary terminals, and to the secondary terminals we have the load. And this is where the secondary terminals are. So, this is E1, and of course, this is Eg, the generator voltage. This is the secondary terminal voltage E2. Now, here we have, let me introduce the dot polarity. This is the dot polarities. This is 1:n. This is induced EMF due to the mutual flux on the secondary side. induced EMF on the primary side due to the mutual flux. There is of course a mutual flux which links the two coils, primary and the secondary. There is a current here IP. Now there is a secondary current I2. Now there is a current here I0, which gets split up into two components, IM the magnetizing current, IC the core loss component through RC, and there is I1 the current drawn from the source, the primary terminal current. And of course, there are voltage drops across each of the components, ER1, E sigma 1, and as the current in this direction we have E sigma 2 and the voltage across this. So, this is the practical transformer. Now, let us draw the phasor diagram for this practical transformer. It looks pretty complex, but it is not actually so difficult to draw the phasor diagram. In fact, we have in parts drawn the phasor diagram. We have drawn the phasor diagram for the ideal transformer portion. We have drawn the phasor diagram for the ideal transformer plus the core loss and magnetizing component portion. Now, we have to include these two. So, let us start from the phasor diagram, the ideal components. We shall first of all have the two axes, which is the x and the y axis, which are called the alpha beta axis in the spatial coordinates. Okay. Now, let us take the ideal transformer portion. Now, if you look at the ideal transformer portion, the primary voltage is EM1, the secondary voltage is EM2. The dot polarities are shown here. EM1 and EM2 will be in phase. So, therefore, we have EM1, EM2, both of them are in phase, and let me draw that portion in this color. Then the secondary current I2 will be in phase with the primary current IP. Now, as it is stepped down from the way we have drawn here, because EM2 is less than EM1, the current I2 will be higher than IP. So, therefore, the current will be lagging, and this would be I2, and IP will be somewhere here, let us say. They both will be in phase, and the flux phi m is going to be 90 degrees lagging the induced voltages, because induced voltage is equal to n d phi by dt. We know, we have seen that before from the Faraday's law of electromagnetism. Now, IPI2 is going to lag the induced voltage EM2 by the amount of lag which is produced by all the reactances, impedance put together, that is the leakage, R2 and the load impedances put together. Now, this would be the portion of the phasor diagram that we had obtained for the ideal. Now, on including the core loss component, the magnetizing component, we know that EM1 and the voltage across RC will be in phase, because IC is the core loss component which will be in phase with EM1, and IM is the magnetizing component which will be 90 degrees lagging with respect to EM1. Now the magnetizing component is going to have a much higher impedance with respect to the core loss component. So let us put the core loss component of the current IC like that, and let me put the magnetizing portion of the current IM here, and I naught is as shown here. This is I naught. So we see that I naught, which is the resultant of IM and IC, and that is lagging EM1. Now the current I1 is the vectorial sum of IP and I naught. The vectorial sum of IP and I naught will be I1. So IP is here. So let us draw the parallelogram. That is, we draw the parallelogram for so this is I1. That is, IP plus I naught will be I1. So this is the primary current I1 at the terminal. I2 is the secondary terminal current. Now what is E1? The terminal voltage E1. Terminal voltage E1 is the voltage across this terminal, which is EM1, plus the voltage across the leakage reactance, plus the voltage across the winding resistance R1 of the primary. All these are vectorially added to obtain E1. So we have EM1 here. So to EM1 we add, let us say, IR1. Now IR1 will be in phase with I1. Now let us now draw parallel to I1. So I will say this is the I1 direction. So along this I1 direction, we have a voltage which is I1R1, and 90 degrees rotated, which is j omega L sigma 1 into I1. That is 90 degrees. This is 90 degrees. So EM1, this is EM1 plus x sigma 1 I1 plus I1 R1, all put together will give you the vector E1, the phasor E1 in this case, because we are talking of RMS quantities. So, this would be the E1 phasor, this one. Now, we need to know what is the E2 phasor. We know that the secondary side EM2 is along this is the EM2. Now, EM2, look at the directions at a instant, because the current is flowing in this direction. EM2 minus the drop across the secondary leakage reactance minus the drop across secondary winding resistance IR2 is going to be E2. Now, let us take the current I2, and from the tip of EM2, let us draw an axis which is parallel to I2. So, this is I2, and let us have an axis which is parallel to I2. So, we have an axis which is parallel to I2, and this is called the I2 direction. So, along this I2 direction from here, we have minus R2 I2. So, this would be the plus R2 I2, therefore, we have to go in the minus direction. This is R2 I2, this is minus R2 I2 direction, and minus, so that is from this direction taking 90 degrees anti-clockwise would be the plus J sigma 2 direction of the voltage drop. We are now subtracting that, and therefore, we have X sigma 2 I2. So, EM2 minus I2R2 minus sigma X sigma 2 I2, and that is going to give you E2. So, this would be E2. So, this would be the phasor diagram of this complete equivalent circuit of the transformer. Though in the completed form the phasor diagram looks complex, but it is not so. You can start from the idealized transformer, which is how we evolved the circuit, and then the core loss component, the magnetizing component, and then follow it up with the leakage components and the winding resistance components that we added to get the complete phasor diagram of the transformer. Okay. So, now, because we will be using this quite frequently, I am going to copy that. Let us go to the next topic. Okay, the next topic we want to discuss is on the per unit values, the per unit values. Normally, it is advantageous to normalize the various parameters of the transformer. That is, you have the resistances, the impedances, the voltages, the currents. All these could be normalized with respect to some base value, and we have what is known as the per unit values, that is you have the maximum value as 1 in terms of the per unit values, or percent values, that is the maximum can be 100. So, if any value is 80%, then we say that it is 0.8 times the base value. So, that would give you a platform for comparison of the various transformers and of various ratings. Now, in the case of the per unit values, the nominal voltage of the transformer, that is E1 nominal, is considered as the base voltage. For the primary, and E2 nominal, that is whatever is the rated, as the base voltage for the secondary. This is for the primary and this is for the secondary. The VA rating nominal, VAN, which is the nominal VA rating, the apparent power rating of the transformer, VA rating is considered as the base apparent power. And therefore, from this the nominal current is nothing but the VA nominal by E1 nominal, if it is the primary. This would be taken as the base current for the primary, and the base impedance Zn, or the nominal impedance, is, if it is for the primary side, E1 square by VA nominal. If it is for the secondary side, that is, if we say this is Z1n, and Z2 nominal, the base impedance on the secondary side would be E2n square by VA nominal. These could be taken as the base values to obtain the per unit values of the transformers. Let us illustrate this with a simple example. Now, consider a transformer which is rated for 250 kVA transformer, which has a primary voltage of 4160 volts to a secondary voltage of 480 volts, and it is a 50 hertz operation. So, this is the primary and this is the secondary rating. Okay. So, now the question is, we need to calculate base impedance. Calculate base impedance. Now, on the primary side, first let us take the primary side. So, on the primary side, the base impedance is E1n square by VAN, which is 4160 is the rating of the primary square divided by 250 into 1000 VA, which is 69 ohms. Now, for the secondary side, the base impedance for the secondary side Z2n is secondary nominal voltage square by VA nominal, which is 480 square by 250 kilo VA, which is around 0.92 ohms. So, this becomes the per unit, this becomes the base impedance. So, any impedance value divided by the base impedance will give you the per unit impedance. Now, the advantages of the per unit values are many. Actually, if you see the relative values of the reactances, the core loss component, the magnetizing component, the leakage component, the winding components, the relative values of these with respect to different ratings of the transformer, all these comparisons can be made very well with the per unit values or the normalized values. Now, to give you an idea, let us say we have these parameters in the circuit, that is this equivalent circuit has this following parameters: R1, R2, these are the winding resistances of the coils, and we have X sigma 1, X sigma 2, the leakage reactances, Xm, this is the magnetizing reactance, Rc, this is the core loss resistance, I naught, which is the no load current which is drawn from the primary source. Now, for these circuit elements, what are the per unit values? What are the PU or the per unit values? Now, these per unit values are also dependent upon the VA rating of the transformer, but for a very wide range right from 1 kVA to 100 mega VA, the per unit value change is not very much. The change in per unit values is a very small fraction. However, we can have typical values of these per unit values, which will give us an idea of the order of the reactances and the resistances of the typical transformers of that particular rating. So, we have the per unit values for, let us say, 1 kVA to 250 kVA and 1 MVA, that is 1 mega volt amp to 100 mega volt amp. Okay. For these two ranges, the per unit values are given like this. So, for R1 and R2, the per unit values range from 0.009 to 0.005. That is, it is 0.009 at around 1 kVA, 0.005 at around 250 kVA, and one could do a interpolation, linear interpolation for different other VAs in between. And these values vary from 0.005 to 0.002. Per unit values are dimensionless quantities. You see, actually the variation is not much, from 0.009 to 0.005 for 250 kVA variation, and for around 100 MVA variation also 0.005 to 0.002. And the leakage reactances have the per unit values of 0.008 to 0.025. The per unit value at around 1 kVA is 0.008 and at around 250 kVA is 0.025, and 0.03 at around 1 MVA and 0.06 at around 100 MVA. And for the magnetizing reactance, it is around 20 to 30, and for the higher range it is around 50 to 200. For the case of the core loss component, it is around 20 to 50 in the 1 to 250 kVA range, and it is around 100 to 500 in the 1 MVA to 100 MVA range. The no load current I naught that is drawn from the primary source is varying from 0.05 to 0.03 in the 1 to 250 kVA range, and 0.02 to 0.005 in the 1 to 100 MVA range. This is a very useful table which you can use for comparing various rating transformers. For example, let us take a transformer . Let us take a transformer and try to evaluate from the per unit values the order of magnitude of the various parameters, that is the reactances and the resistances in the equivalent circuit of the transformer. Again, let us say the rating of the transformer is 250 kVA with a primary to the secondary voltage ratio of 4160 volts to 480 volts, 50 hertz distribution transformer. Now, for this transformer, let us try to find the various values of the reactances from the per unit values of the previous table. Now, first let us find out the base impedances. Now, Z1n base, which is nothing but 4160 square by 250 VA, which is 69 ohms, and Z2n, that is the base resistance of the secondary side, is 480 square by 250 kVA, which is 0.92 ohms. Now, these are the base impedances. Now, using these base impedances, we now evaluate the various components as given in the table, in the previous table. So, now R1, we look at the table and we are talking of the 250 kVA transformer, and therefore, let us take these values for consideration. So, R1 and R2, the per unit values is 0.005. So, R1 is 0.005 into, on the primary side, the base impedance is 69 ohms, which is 0.35 ohms. R2 is again 0.005 and the base impedance on the secondary side is 0.92, which gives you 4.6 milli ohms. Now, the leakage reactance X sigma 1. Now, if you look at X sigma 1, the per unit value is 0.025 for a 250 kVA transformer, 0.025 into the base impedance for the primary side, which is 69, will give you 1.7 ohms. And X sigma 2, secondary side leakage reactance is having 0.025 into the base impedance on the secondary side, which gives you 23 milli ohms. Now, XM, the magnetizing reactance. So, the magnetizing reactance has a per unit value of 30, which is 30 into, on the primary side, 69 ohms is the base impedance, which gives you 2070 ohms, or roughly about 2 kilo ohms. And RC has a value of 50. So, it is 50 into 69, which is 3450 ohms. It's approximately 3.5 kilo ohms. Now, this is the real impedance values, at least the order of magnitude or approximate values of the real impedance values of the transformer, which we can now write here. This is having a value of 0.35 ohms, having a value of 1.7 ohms. This is around 2 kilo ohms. This is around 3.5 kilo ohms. This has we found it as around 23 milli ohms. This is 4.6 milli ohms. Okay. So, this has a voltage of 4160 volts to, on the secondary side, approximately 480 volts. This is the, and the turns ratio N, which is equal to 480 by 4160. So, this way, given a rating of the transformer, if this is the power rating of the transformer, looking at the table of per unit values, one can obtain the order of values of the various resistances and the reactances of the transformer, and this will give you a comparison between various transformers from various manufacturers of the same rating. Now, the next point we would like to discuss is the equivalent circuit itself. Now, we see that this equivalent circuit, the complete equivalent circuit, can be simplified under certain operating conditions. So, we have two major operating conditions. One is under open circuit condition, and the second is under loaded condition. Loaded condition. This is considered as no load operation. So, under no load, the secondary load here, the secondary load is removed. The secondary is open circuited. Under loaded condition, the load is connected across the secondary terminals. Now, let us take the case of open circuit condition, which is the no load. So, under no load, some of the parameters will vanish. So, there is no I2, which means I2 becomes 0. So, if I2 becomes 0, IP being this being an ideal transformer, IP becomes 0. So, only what is drawn from the primary source is I naught. Now, as I2 is 0, the presence of this leakage reactance and the winding resistance is not needed. And as these winding resistance, the leakage reactance is very small, the I naught into the impedance drop will be very small compared to the voltage which is applied. These can be neglected, that is R1 and X sigma 1 can be neglected, which means the equivalent circuit under no load condition could be simplified as this: just the magnetizing loss component followed by the ideal transformer, with the secondary just open circuited, dot polarities 1:n. So, this of course is E1 or EG. So, you have XM, RC, there is IC, IM, I naught. There is no current flowing through any of these. IP equal to 0 and I2 equal to 0. This is E2. So, this is how the equivalent circuit would reduce to under no load conditions. Now, if you look at the condition under load, there is going to be I2 flowing, that is under full load condition. So, if you look at the full load condition, let us go to the next page. I2 is going to flow through it, the full rated I2. IP is going to be I2 into N. I naught is going to be a very small percentage of IP. That is, I naught is going to be very, very less compared to IP, and therefore, I naught can be neglected. So, which means XM and RC can be neglected under full load conditions. So, under the full load conditions, we have EG, R1, X sigma 1, the ideal transformer, secondary side, X sigma 2, R2, and Z2, whatever the load is going to be, or we will call it as ZL instead of Z2. So, we call it as ZL. This is 1:n. In fact, everything can be taken onto the primary side by the conversion, and then we can make the following modification. We remove this transformer here. We put the transformer on this side. So, here I 2 is equal to 0, this also I p equal to 0, and we join it here. Now, these values would be pi n square divided by n square. This would be the impedance that one would see. So, which means the resistance, the impedance as seen from the source Z1 equivalent as seen from the primary side would be equal to R1 plus R2 by n square, that is the resistance component, plus x sigma 1 plus x sigma 2 by n square, that is the reactive component as far as the transformer impedances are concerned, internal impedances are concerned, plus ZL by n square, that is the load component. So, this is the load component. Of the transformer. So, it just reduces to R plus jxp, and that would be the equivalent resistance of the transformer. And now, we should attempt or obtain the parameters, the various parameters of the equivalent circuit. So, if from the measurable quantities we are able to obtain the various parameters of the equivalent circuit, then our analysis, then our discussion on the transformer would be complete. So, going back to the equivalent circuit, we perform two tests on the transformer. One test is called the open circuit test. So, we said that when you are doing the open circuit test, the secondary side is open, which means I2 is 0, which means IP is also 0. This implies that I do not need these reactances under open circuit conditions. We just saw that these become very negligible. So, therefore, under open circuit condition, this becomes the equivalent circuit that we will be looking at. IP will not exist and this will not exist. Now, what are the things that we can measure? So, under the open circuit test, we measure E1. E1 is measurable with a voltmeter connected across the terminals of the transformer. E2 is measurable with a voltmeter connected across the terminals of the secondary of the transformer, of the practical transformer. Then we can also measure I0. I0 can be measured by connecting an ammeter in series, that is we connect an ammeter, in series to measure I0. This is an ammeter which connects Now, the voltage here is measured with a voltmeter. We also connect a voltmeter here to measure E2, or let me use the following symbols. An ammeter, a voltmeter, and a voltmeter. Okay. Then we could do one more thing. We could measure the active power that is taken from the source by connecting a wattmeter at the primary side. This measures the active power that is taken from the source. So, we will be obtaining P, which is obtained by connecting a wattmeter. So, you need two voltmeters, one ammeter and one wattmeter to do the experiment, which is the open circuit test. So, once you have this, the VA is given by E1 into I naught. E1 into I naught is the VA which is drawn from the source, and the reactive power VAR is given by root of VA square minus P square, where P is the active power measured in the wattmeter. And now, based on this, we can obtain RC, which is equal to E1 square by P, and we can obtain XM, which is E1 square by Q, and we can obtain N, which is E2 by E1. So, based on these measurements, these parameters are obtained. These measurements could be taken, around 5 readings can be taken for these measurements, and an average of that found out, and that could be used for making the calculation here to improve the accuracy of the measurements. So, now we have obtained the core loss component, the XM, which is the magnetizing component, and the turns ratio from the open circuit test. We now perform the next test, which is the short circuit test. So, in the short circuit test, what is done is the secondary is short circuited. So, as the secondary is short circuited, we do not apply the full nominal voltage to the primary. The voltage EG that is applied is a very small amount. In fact, it can be applied through a variable voltage source or a auto transformer. You just keep increasing the voltage till the rated current flows through, or the nominal current flows through the secondary, and take the measurements at that time. The measurements can be taken quickly so that the transformer does not heat up. So, under the short circuit condition, we see that the IP will be much higher than the I naught, and therefore, they can be neglected. So, these portions will vanish as they are negligible. And we can do one more thing, as I was saying. These impedances can be transferred onto this side, which means that we remove these and transfer them onto the primary. So, we include and then a short here, IP equal to 0, I2 equal to 0. So, as this is equal to 0, this ideal transformer could also be removed. So, equivalently we have just this portion as the equivalent circuit now. This would be x sigma 2 by n square, this is R2 by n square. So, you continue to keep the wattmeter here, wattmeter. We continue to keep an ammeter, keep the ammeter here, that is we need a ammeter there, and then we measure the voltage across the primary through a voltmeter. So, we measure the voltage through the voltmeter across the primary. So, these are the changes that happen when you do a short circuiting of the secondary side. So, this is called the short circuit test. So, here we are measuring E1 with a voltmeter, you are measuring I1 again with a voltmeter, and you are measuring the active power which is drawn from the source again with the wattmeter. Now, this we can use to obtain the rest of the parameters. Now, ES, that is E1 divided by I1, the voltage across the primary divided by the short circuit current will give you ZP. So, ZP is obtained. Now, RP is obtained from the power that is measured under short circuit condition by I1 square, because I1 square into R will be RP, which is R1 plus R2 by N square, and XP, X primary side, is given by root of ZP square minus RP square, which is X sigma 1 plus X sigma 2 by N square. Okay. So, this is RP and this. So, RP gives you the total reflected primary reflected winding resistances of both the primary and the secondary as seen from the primary side. XP gives the total leakage reactances of both the primary and the secondary side reflected onto the primary side as seen on the primary side. So, this gives you the leakage reactance and this gives you the equivalent winding resistance. So, short circuit test can be used for finding these two parameters. As N is known, one can also find out the other parameters. R1 can be measured directly knowing the number of turns, or measured directly from a multimeter, then R2 can be found knowing N, and these, in this case we have to take this as a equivalent secondary leakage or the primary leakage as seen on the primary side. So, with this we know about the transformer, equivalent or complete equivalent circuit, the phasor diagram, how to analyze it, and then what are the parameters that come into the imperfect or the practical transformer. We also discussed about the per unit impedances which are used for comparing the various transformers of various ratings, and finally we have done two experiments, which is the open circuit test and the short circuit test, to obtain the parameters, parameters of the equivalent circuit of the transformer as explained before, and these parameters can be plugged in from the measured quantities, and they will give you the model of the transformer, which can be used for further analysis with other circuits. In the next class we will take up the concepts of DC motor and generator. Thank you for now.